In this video, we're going to be taking a tour of the electromagnetic spectrum. It's just an overview of the electromagnetic spectrum. Nothing very complicated, but it's important to have a good understanding of the electromagnetic spectrum and how electromagnetic energy waves differ from mechanical waves like sound waves. Well, electromagnetic energy waves basically are the energies that are released by atoms. The energy that is radiated from atoms, and it travels at approximately the speed of light, which is called c. C is the symbol that stands for the speed of light. And the speed of light in a vacuum, that means through nothing, the speed of light through the nothingness of outer space is about 2.99 times 10 to the 8th meters per second. And that is fast. A lot faster than sound. Sound travels through air at about 340 meters per second. Light travels at approximately 2.99 times 10 to the 8th meters per second through the nothingness of outer space. And that's important to remember also. Electromagnetic energy doesn't need a medium like sound does. It travels best through the nothingness of outer space. As a matter of fact, if you pass a light wave through air or glass or water or some other transparent material, it actually slows the light wave down a little bit, and that's why lenses work, which we'll talk about later. But the important thing to remember about the electromagnetic spectrum is that all forms of electromagnetic energy travel at the speed of light, which is 2.99 times 10 to the 8th meters per second through the vacuum of outer space. Very fast. Another important point to remember about electromagnetic energy is that it comes in a variety of different wavelengths. It comes in a vast array of different wavelengths. And you can see that in this diagram. In this diagram, you can see that the wavelengths of electromagnetic energy extend from very long wavelengths down to very, very short wavelengths. And an important point, the shorter the wavelength, the more energy the wave is carrying. Short wavelengths down here have more energy than the longer wavelengths up in this part of the spectrum. The shorter the wavelength, the more the energy, and that just stands to reason. That's logical. If you can imagine lots of wavelengths close together, very short wavelengths as you see down here, striking a surface, well, the more waves that hit a surface per second, the more energy is delivered to that surface. So if you spread those waves out so you have longer wavelengths, then the fewer wavelengths you have hitting the surface every second, the less energy. So keep in mind that in the electromagnetic spectrum, shorter wavelengths mean greater energy. That becomes important when we look at the types of waves that are associated with the electromagnetic spectrum. Well, starting down here on the right-hand side, somewhere between 1 meter and 100 meters, we have different forms of radio waves. That would be radar, TV, and AM and FM radio. Those waves that you very commonly associate with, well, say, entertainment and being able to detect aircraft and other objects far off. Radar, TV, and AM and FM radio. So those wavelengths are actually fairly long wavelengths. And then right next to them, and this is just about at the 1 centimeter mark, we have microwaves. Microwaves, those are produced by like a microwave oven. As a matter of fact, microwaves, you notice how close they are here with radar waves, very close to them. Microwaves were actually discovered when the person who discovered radar had a chocolate bar in his pocket, and he was standing next to the magnetron that was operating. The magnetron was generating radar waves, and they noticed that the chocolate bar in his pocket melted. So microwaves used in microwave ovens, actually the device that produces them was actually developed during the Second World War when they were trying to develop radar. Infrared energy, which is slightly shorter wavelengths than microwave. Well, infrared represents basically heat energy, And heat energy is absorbed by objects, and it causes molecules to move faster, and that's why the temperature of an object increases. So that's infrared. And I'm going to skip this intersection right here for just a minute. We're going to jump down past it, and we're going to look at UV, ultraviolet. Your eyes aren't sensitive to ultraviolet. The wavelengths are too short. Infrared, your eyes aren't sensitive to infrared either. The wavelengths are too long. So ultraviolet and infrared are separated by this section in the middle, and that's the visible light, and we'll talk about that in just a minute. By the way, infrared energy, your eyes may not be sensitive to it. However, rattlesnakes and other pit vipers have an organ in their face that's sensitive to infrared energy, and that's why they can follow warm-blooded creatures so that they can strike them and eat them. Ultraviolet light, well, a lot of flowers reflect ultraviolet light, and bees' eyes have evolved to be sensitive to ultraviolet light. Your eyes have evolved to be sensitive to this light right in here, which we call visible light, and again, I'll talk about that in just a minute. X-rays, you notice we're getting down into shorter and shorter wavelengths down here. X-rays are fairly high energy waves, so they can be dangerous. That's why when you go to the doctor's office, they always limit you to the amount of X-rays that they expose you to in a certain time period. It's also why the person who gives you the X-rays puts on a lead vest or a lead apron when they're giving you the X-rays. It's because they don't want to be exposed to them. Because X-rays are very high energy and they are penetrating rays. They go through tissue, slowed down through more dense material like bone, and that's how they can show bones up on an X-ray that's being taken. So X-rays can be dangerous, fairly short waves. And then of course you get into these waves down here, the very short wavelengths, very high energy wavelengths, the gamma rays, and these are bad waves. These are the ones that are produced by high energy nuclear decay. Say for instance a fission reaction will produce gamma rays. These are the waves or rays that are very short in wavelength. They go into living tissue. They can damage DNA. So these are bad waves, very high energy, bad stuff. Alright, that's just a basic overview of the electromagnetic spectrum. Let's talk about this very small section of the electromagnetic spectrum right in here, between somewhere around 400 billionths of a meter up to just a little bit over 700 billionths of a meter. A billionth of a meter is a nanometer, by the way. So just about from 400 nanometers up to just over 700 nanometers, we have this part of the electromagnetic spectrum referred to as visible light. These are the wavelengths that your eyes are sensitive to, and it extends from the longest wavelengths of visible light, which are in the red part of the spectrum, and it extends all the way down to the violet end of the spectrum, which are shorter wavelengths. And it is a very small portion of the electromagnetic spectrum. Your eyes are only sensitive to an extremely tiny portion of the electromagnetic spectrum that you see right here, where it's expanded from red, orange, yellow, green, blue, indigo, and violet. Those are the colors represented by different wavelengths of the visible part of the electromagnetic spectrum. But let me point out, you know, if you think of this this visible light, there are not just certain colors. There is almost an infinite variety of wavelengths between the red end of the spectrum and the violet end of the spectrum. So there are a constantly changing number of shades, almost an infinite number of shades, because each shade of each color represents a particular wavelength, and there's almost an infinite number of different wavelengths. So you can think of that as, well, here's a good comparison. If you look at a piano keyboard, you can produce one note with one key, and then you can produce another note with another key that's next to it, but there's no notes that are in between. Well, that's not like light. If you can draw the comparison between sound and light, if you look at a trombone has a slide on it that produces a constantly changing series of wavelengths of sound. Well, light, from the red to the violet, represents a constantly changing, a constant continuum of different wavelengths. It's not really separate individual wavelengths. It's a constantly variable series of wavelengths, from longer wavelengths in the red down to shorter wavelengths in the violet. It's how your eye responds to each wavelength, each frequency, that your body interprets as a particular color. And basically, there's an overview of the electromagnetic spectrum. Things to remember again: remember that the electromagnetic spectrum is energy that's released by atoms, that's given off, radiated by atoms. It travels through a vacuum of outer space at the speed of light, 2.99 times 10 to the 8th meters per second. Remember that the wavelength and the energy of the wave are inversely proportional. The shorter the wave, the greater the energy. Also, remember some very common types of electromagnetic energy: damaging short waves on the gamma ray into the spectrum, X-rays, a little bit longer than the gamma rays but still very dangerous, ultraviolet, your eyes aren't sensitive to it, but bees' eyes are sensitive to it. The visible part of the spectrum, your eyes are sensitive to that. The infrared energy, or IR energy, represents basically heat energy. And then microwaves, radar waves, radio, which consists of perhaps TV, AM, and FM. So those are the parts of the electromagnetic spectrum you should remember. Also remember that the visible light extends from red, orange, yellow, green, blue, indigo, and violet, and represents a continuum of wavelengths that your eyes are sensitive to. And the visible light is only a very small portion of that electromagnetic spectrum.